Good morning. My name is Phil Westmoreland, and I'm delighted to introduce Stephen Klippenstein as our plenary speaker this morning. Stephen's background was, he actually began in chemistry and mathematics, but he took his doctorate at California Institute of Technology with Rudy Marcus, as in RRKM theory, in 1988, had 11 years as an educator at Case Western, and then moved into the U.S. Department of Energy National Laboratories, first Sandia and then at Argonne, where he's been since 2005 and is Distinguished Research Fellow. Our good friend, the late Adel Seraphim, used to love to invoke the story, says that if somebody tells you that there are billions and billions of stars in the sky, they'll look up and say, wow. If you tell them there are billion grains of sand on a beach, they'll look at the beautiful beach and say, wow. He said if you tell them you're trying to understand how fire burns, they'll say, light a match. The reality is that combustion, these beautiful flames that we love, are made up of billions and billions of molecules doing elegant dances, and Stephen has brought powerful tools to understand the elegance and the beauty of these interactions. That's what he'll be talking to us about today. So Stephen, welcome.
Thank you, Phil, for the kind introduction. Thank you, Peter and Assad, for the opportunity to speak here today. We've seen a progression in these plenary lectures. We started with a beautiful lecture by Thierry Ponceau on CFD and combustion instabilities. Then we had lectures on combustion synthesis and soot particles, where we introduced a little bit of chemistry. And then we had the lecture by Bob Key on fuel reformulation and methane conversion to useful fuels. And there we saw quite a bit more combustion, even started getting into some molecular chemistry. Today I'm going to really be essentially all chemistry. That's not to say that I think that CFD is not important. This is the area that I work in, and I think one of the great and really spectacular progress in the last few years is the fact that now we can do realistic simulations where we treat both the CFD and the chemistry at a level that is highly accurate and has some predictive nature to it. And so as we get to that point, now it becomes more and more important to really get the chemistry part right so that it can be coupled in meaningful ways with the CFD. As Phil said, I'm a theoretical chemist. And if you look at what the progress in theoretical chemistry is, that also has been really spectacular. It's made a real transformation from being an empirical science to a highly predictive science. If you look at what was done 20 years ago, theory was just used to try and interpolate and extrapolate experimental data from conditions of observation to the conditions of use and relevance to combustion. But what I'm going to try and convince you today is that theory by itself can predict rate coefficient thermal chemistry to the kind of accuracy that is rivaling or perhaps even exceeding experiment when it's done at its highest levels in many instances. And if you start to believe that, then you immediately start to think, wow, there's tremendous opportunities for theory. And those opportunities, though, need us to start scaling and doing a lot more calculations and make better use of our computational facilities. So I'm going to try and give you some indication of why I have this really optimistic vision for the future of theoretical kinetics, and thinking about how maybe start people here in the audience thinking about how can we really make full use of theoretical kinetics. When you think about chemical modeling, one of the things you'll observe, if you pick up any issue of combustion and flame, nowadays you'll find half or more of the articles have some form of a chemical model. It's a real explosion in chemical modeling in this community, at least in combustion and flame is any example. And you might ask, well, why is that? And you look at it, well, there's been all sorts of societal drivers for trying to improve and and decrease the number of pollutants, increase the efficiency, and just make real advances in combustion in order to solve all sorts of problems. When you think about trying to solve those problems, there's various things, various prospects. One thing is to have new fuels, novel fuels, alternative fuels. And so if you look through combustion and flame, you find lots of studies of various different biofuels, with the idea that by having renewable fuels, you will reduce the CO2 emissions, the net CO2 emissions by recycling things. Another thing that we see a lot of interest in is in developing more efficient engines and more efficient combustors. And if you look at almost all those schemes, as Thierry Boinceau was describing, it's all about low temperature combustion. And as you go to low temperatures, you have a lot more dependence on the chemistry. And so when you try and implement those schemes, there's a lot of interest then in better understanding of that low temperature combustion. And a lot of that work deals with reference fuels, standard fuels, so that we can really understand what would be going on in our engine at lower temperatures. So things like heptane and isooctane and toluene are still under study in the chemical modeling community. When you look at how molecules burn and how mechanisms get developed, it's all hierarchical. You sort of start with the mechanism for a small molecule, and those mechanisms are subcomponents of mechanisms for bigger molecules, and so on. And so as a result, there's still a lot of work on what you might think of as the foundational fuels, the small molecules, C1 to C3 hydrocarbons. And then lastly, we're still a lot of interest in pollutants, particularly soot and PAH formation, and trying to develop mechanisms for those are important. It's interesting to think for a second about some of the ways that people are trying to use mechanisms, and some of the ways that these societal drivers are driving our funding agencies. So in the United States, the Department of Energy, the applied arm of the Department of Energy, has started a new program to try and co-design fuels and engines, and they're doing this for both spark ignition engines and compression engines. And in the spark ignition engines, one of the first steps has been to try and come up with a pool of candidate molecules that you might think of considering. And that pool consists of these 20 molecules in their first pass. And one of the things that team is trying to do is then trying to develop chemical mechanisms for all of these fuels. The idea being that if you have a chemical mechanism, then you can better understand how you can use an engine, whether it will function, whether it will be an appropriate fuel or not, and what kind of conditions you could run your engine under for those fuels. You try and think about trying to develop a mechanism for this. It's an enormous problem for each of those fuels. In general, a mechanism for a given fuel of this sort of size might have 500 species and 5,000 reactions. So there's a lot of work involved. To try and understand why there's so many, let's start by just thinking about the first step in the reaction. How do you start the process of going from fuel to CO2 and water? Well, the first step generally is to have some kind of abstraction reaction. In an abstraction reaction, you have sort of 6 standard abstractors in chemistry: OH, O, O2, HO2, methyl, and H. Those 6, if we think about trying to develop mechanisms for all those, we've got 6 abstractors. Each one of these molecules has about 8 different sites where you could abstract from. So, for example, in 2,4-dimethylhexane, you could abstract from this carbon, that carbon, any one of these different carbons. So the net result, just thinking about the abstractions, just thinking about the first stage, conversion of the fuel to a radical, you get about 1,000 different reactions you have to think about. So Bill Pitts, for example, is working on this project. He has to try and come up with rate coefficients for those 1,000 reactions, just for the first stage, just for understanding how we get the fuel radical. Of course, things are much more complicated than that. I want to take a few minutes. This is going to be a somewhat detailed slide, and I apologize for that, but I think it's worthwhile to try and give you some perspective on what's involved in the whole modeling process, so that you can see how the different theoretical things I'm going to show you contribute to this overall modeling effort. I just described to you how many reactions are involved in just the first step, the abstraction from the fuel. And I said that's the general procedure for producing the radical. There's also, at higher temperatures, you sometimes just simply have a molecular decomposition to two radicals. But either way, the first step in the process is formation of a radical. And when thinking about combustion, the key thing is to try and understand how we get chain branching. How do we get converted from one radical to two radicals? And that's a complicated problem in general. In almost all cases, there's two different kinds of pathways you can follow. One pathway is operative at high temperatures, and another pathway is operative at low temperatures. Low temperatures being about 1,000 Kelvin and lower, and high temperatures being the reverse. In general, the high temperature pathways are what correspond to the largest and the majority of the conversion of the fuel. And so the high temperature pathways is really the foundational part of combustion. And that's where we've put most of our work in theoretically. But the low temperature pathways are really important for understanding things like NOx and stability and whether or not your engine is going to function. And so there's a lot of interest and focus on that, especially now as we find that the low temperature combustions are probably the way and are being considered as the driving force for improving efficiency. So let's look through those two different pathways a little bit. At high temperature, you have enough energy to take this radical and simply decompose a bond in that molecule. It's called a beta scission. You just break a bond in that, and you produce then another radical and an unsaturated hydrocarbon, an alkene in general. That process repeats itself until you get down to H and methyl radicals, and other radicals perhaps that can't be further unsaturated like propargyl. But the main two are H and methyl radicals, and that's why those two radicals are some of the key radicals for the abstractions. You think then about the reactions of those two radicals. If you have enough energy again, and this is really part of why this is the high temperature pathway, then H plus O2 can react to make O plus OH. We've gone from one radical, our starting abstractor, to two radicals, and so we've done a chain branching. That then propagates into an explosion, and we just go repeatedly through this cycle with these radicals going back and abstracting and going through, and so you have a complete conversion of the fuel then in the end. The methyl has a similar sort of process. Here in this case, though, there's a competition between chain branching and a separate channel that's not chain branching. Another thing that we find, that one of the co-products of all these dissociations are a number of unsaturated hydrocarbons. Those unsaturated hydrocarbons contribute to hydrocarbon growth, to PAH formation. Two of the most important are propargyl, which is a key path, which self-recombination provides the dominant path for benzene in most situations. And acetylene is a key component of the growth from benzene to multi-ring aromatic hydrocarbons. And so your mechanism must include, in general, if you're trying to understand pH and soot formation, you must include a whole host of reactions here. You have to have all the reactions. I've only listed the first couple. There's a whole set of reactions that correspond to then conversion of all these small species, all the reactions corresponding to this decomposition. And these decompositions are not happening for just one radical. These abstractions at different sites make maybe 10 different radicals here. And so you start to see how there's an explosion of the number of reactions you have to think about. And the other pathway, the low temperature pathway, what happens is you don't have enough energy, you don't have enough heat to decompose the radical. So instead what happens is the radical and O2 combine. You make an RO2 radical. The RO2 radical has the radical on an oxygen. The oxygen radicals are not particularly reactive, but if you have an internal hydrogen abstraction, you can transfer that radical back to a carbon site, and a carbon radical can then add another O2. That O2 QOH species can then have have another H transfer, which leads to a bond scission. We get one radical here, and then we have a further OO bond scission here that leads to a second radical. So we end up getting two radicals back from our starting radical again. So we've got chain branching again. One of the interesting things about this low temperature pathway is that it has something that we call negative temperature coefficient behavior. What that means is that as you raise the temperature, the rate of this explosion actually decreases. And the reason for that is that as you increase the temperature, in general, you've got a branching between going through this pathway and going through this pathway to form alkene plus HO2. The RO2 can simply decompose to alkene plus HO2, or it cannot do this internal H abstraction and O2 addition. As you raise the temperature, the probability of going through this pathway increases, and that then shuts off this chain branching process. Eventually, as you keep raising the temperature, this HO2 starts to do interesting chemistry through hydrogen peroxide, and you start to get opportunities for this chain branching again. But for a limited range of temperature, you have a case where the rate coefficient decreases with increasing temperature. One of the interesting things that we're hearing about in this symposium is there's actually opportunities to add a third O2 to this. Niels Hansen and Manny Sarathi and Philippe de Gaulle were talking about the possibility of having a third. And you might imagine that just keep on going and leading to analogous chain branching pathways. Theory has made major contributions to understanding all this. Our knowledge of what reactions are real and just the general reality of this whole scheme that I'm putting up here is derived from many years of careful theoretical and experimental work. I've highlighted in green here a number of people that have contributed recently to various parts of theoretical modeling for this. Bill Green, Kevin Van Giem, Richard West, John Simi, and many others have been doing high-level calculations of abstraction rate constants. And one of the key things they've been doing recently is automating that process so that people like Bill Green are calculating hundreds and thousands of abstraction reactions routinely now. The low temperature pathways, Joe Bazzelli has done a lot of work on mapping out the potential energy surfaces. Bill Green, Kiri Miyoshi, and Tony Dean have done a lot of work in turning representations of the potential into rate coefficients for these processes. And Mike Franklak has done a lot of work on pH pathways. Alex Melville and Carlo Cavallati have also done a lot of work. And in this list of people, of course, this is a very incomplete list. It's a large community that has contributed greatly. I'm just trying to highlight some of the leading players. We've done a lot of work on various aspects. One of the things that we try very hard to do is to do very high accuracy studies of prototypical cases. So our studies have tended to look at smaller molecules where you can do really good things and then build. The community can build from that knowledge to understand the accuracy, improve the accuracy for larger systems. I'm going to tell you mostly about these small molecule studies because that's what I do, but it's important to realize that those studies can be used to propagate into better understanding of larger species. Before I get into the theory, I think it's worthwhile to summarize what the sort of standard procedure of developing a chemical model is. We have this big mechanism. Where do we get all the parameters? The parameters are thermochemical properties for all of our molecules, reaction rates, temperature and pressure dependent representations of the reaction rates for all the reactions that convert one molecule to another or set of molecules, and transport properties. It's such a huge database, we can't possibly determine everything from first principles or from experiment. And so the people that do the modeling generally have programmed up rate rules, empirical rate rules that are developed by consideration of specific studies. Because there's lots of qualitativeness to those rate rules, lots of uncertainties to those rate rules, you don't have a mechanism that necessarily is going to quantitatively reproduce reality when you first try and simulate things. And so there's a lot of work in the community to take the mechanism that they first developed and then calculate and predict and model various observables that one can measure with experiment. The standard observables that they focus on are ignition delays, flame speeds, and species profiles. And they measure those at various temperatures, pressures, and various stoichiometries. So the first stage in the modeling after putting together the parameters is to see how well you reproduce these things. And almost always when they first run those simulations, they'll find significant errors in their predictions, significant discrepancies between their predictions and the observables. And then they have to try and figure out why those discrepancies are arising. And the standard approach to trying to discover and improve and remove those discrepancies is to look at sensitivity analysis. Look at how sensitive the observables they're calculating are to their input parameters. And the reactions that have high sensitivity and high uncertainty are candidates for further study. Sometimes you can't really find anything that looks like it has a high sensitivity and high uncertainty. And then the modelers are led to think about whether or not we're missing reactions or missing channels in our reactions. Ideally, once we've identified a molecule that seems to be contributing to our discrepancies, we would then go and do an experiment to try and get an accurate measure a more accurate measure of that rate coefficient or thermochemical parameter. But that experimental process is generally too slow. So most modelers don't resort to experimental elementary reaction rate studies to improve their models. Instead, what they'll do is they'll simply empirically adjust the parameters, and then they'll take their new model, run predictions again, and compare. And they'll just go through this loop over and over again until the discrepancies between the model and the experiment are deemed satisfactory, deemed small enough. Nowadays, some groups are starting to optimize that. People like Frank Black and Wong and Durrani are optimizing this whole process of iteratively improving the mechanism. There's one key shortcoming in that process, though. The mechanism that you end up with in the end is only known to be valid for the conditions of the experiment that you're able to compare with. As Thierry Poinceau was saying in his lecture, we can all calculate methane flame speeds to be 34 centimeters per second. Every model will get something of that order at room temperature and standard pressure. But then when you take those mechanisms and run them at different higher temperature, higher pressure conditions for which there is no experimental data, there'll be a factor of 3 sort of variation in the predictions. Well then, which one is the right value, and what is the real uncertainty in that prediction? To know that, we have to have a very good understanding of how our uncertainties propagate from one condition to another. As the optimization process gives you a very nice reproduction of data, but it's not clear what it does to your extrapolation. Theory provides you an opportunity to try and address some of those issues. You could, for example, take that other conditions where experiment is not possible and run your uncertainty analysis. You can still do modeling, run sensitivity and uncertainty analysis, and take a theoretical calculation and try and improve those key parameters, and therefore decrease the end uncertainties in your predictions, even for experimentally inaccessible conditions. More generally and more commonly, what we just use theory for is to study specific reactions, these reactions that we identify here. Theory is now able to be implemented quickly enough that many modelers, such as the Curran group, will employ, and Fei Chi's group, et cetera, will employ theoretical calculations as part of the mechanism development process. I think it's helpful to try and look a little bit at some of these sensitivity analyses for a sample biofuel. This is a study from Combustion and Flame, 2015, 2 leading modelers, Kern and Pitts. And this sensitivity analysis is so central to the process. So we want to think about, look at what they look like. And what we see, if you look at it for high temperature, what you get is a whole bunch of reactions that are almost all small molecule chemistry. And that's why it's important to really get very accurate foundational fuel chemistry, foundational fuel reaction rates. If we could get all these small molecule rate coefficients accurate to about 20%, and I'm going to try and suggest that's where we're at nowadays in theory, then since there's about 10 or so reactions and sensitivities of about 0.1 or 0.2, your end uncertainty in the ignition delay is only about 10%, which is comparable to what a lot of the experimental measurements of ignition delays are anyways. So in principle, I'm claiming that you should be able to make a completely a priori mechanism that predicts the the ignition delay for standard things to a high degree of accuracy. lower temperatures, the picture is not quite as rosy. There's still a great contribution from theory, but now these sensitivities start to be much more with regard to larger molecules. The abstractions from the fuel, beta decisions of the fuel radicals, molecular decomposition of the fuel. And furthermore, we need to understand these at lower temperatures, and any uncertainty in energy, it just gets expanded as you lower the temperature. And so our ability to predict the key observables is somewhat reduced. Nevertheless, theory is still a great contributor to that process. In order to start thinking about our theoretical predictions, I'm going to show you shortly, it's useful to think of what the generic model is that we use. We like to call it the ab initio transition state theory-based master equation approach. The general thing that one needs in a chemical model, as I was saying, are temperature and pressure-dependent rate coefficients for the rates of conversion from all the different chemical species, chemical molecules. I'm here just showing a schematic plot, just picking a sample reaction with two L's, one W1 and W2, and two separate bimolecular products. And I'm going to try and take you through the process of trying to calculate thermal rate coefficients, phenomenological thermal rate coefficients from the master equation. To do that, we have to think about what happens at a microscopic level, at the microcanonical level, at an energy resolved level. The first thing that happens, one of the things that happens is you have chemistry that goes on. You have isomerization reactions. You have dissociation reactions. If you're starting on this side, you might have an association reaction. So we have to be able to understand these rate coefficients for microcanonical energy resolved rate processes. But another thing that happens is this chemistry is going on in competition with collisions in a bath gas. You have some kind of large bath of nitrogen molecules in a typical combustion simulation. And so those nitrogen molecules are colliding with your molecule while it's reacting and raising it up and down in energy. And we have to model that process in combination with modeling the process of dissociating. The master equation sets up a simple linear equation that treats the time dependence of the populations on a grid of energy levels for each of your species. When you solve that master equation, you get a set of eigenvalues and eigenvectors, and you can make a one-to-one correspondence between the eigenvalues for the chemically relevant modes and these phenomenological rate coefficients that we want to derive. So to implement the master equation, we then need to have rate constants for all the chemistry processes and rate constants for this energy transfer process. Statistical theories, RRKM theory, transition state theory, give you a great way for predicting the rates of chemical processes at an energy resolved level. There have been lots of studies that indicate that we can predict those things at sort of 5 to 10% accuracy. I mean, not that we can predict it, that the RRKM theory itself is accurate to about 5 or 10%, as long as you're not dealing with processes that are too fast. If the rate constants are greater than about 10 to the 12 per second, then RRKM's theory starts to fail. But that's rarely the case, or it's rarely the case that failure is a major problem for the thermal modeling. For the energy transfer, we take a very simple model in general. We're not nearly as well advanced in our treatment of energy transfer. The standard model we use is simply to assume that the probability of a change in energy is just decays exponentially with the difference in energy. And then we have a parameter called the exponential down parameter, the average energy transferred in a single collision. One of the neat progress we've had very lately is to realize that we don't need to make this empirical model. We can actually start to calculate them. And that's something that's coming from work of Aaron Jasper, and I'm going to talk a little bit about that later. But this is the classic model, what we call the ab initio transition state theory master equation model. I don't work by myself. One of the great things about working at a national lab is we have a team of world experts working on closely related aspects of the problem. So just implementing this ab initio transition state theory master equation approach is really the work of a team of 5 of us that are distributed amongst Argonne and Sandia. And I talk with basically all these people on a daily basis as we're trying to probe and think about how to do our calculations better and study specific systems. Many of you may know Larry Harding. He won the gold medal in San Francisco for his work on electronic structure. He's a leading expert on ab initio electronic structure calculations, and particularly multi-reference ones, which are more complex variety. Yuri Georgievsky is a research associate who knows more about chemical physics than I do, and does much, if not all, of our programming work, and has really developed some great codes for us to implement and use in our rate predictions. Aaron Jasper is here today. He's our leader in chemical dynamics and has contributed greatly to our recent progress in understanding how pressure enters into the simulations. And I'm sure almost everybody here knows Jim Miller. He's another gold medal winner, and he's taught me essentially everything I know about combustion chemistry, and is also one of the leading part of our work on the master equation. With all these experts, you might ask what my role is. And I don't really know. If somebody figures that out by the end, maybe you can tell me later. Okay, so now how accurate can we be? There's three components to our calculation: the ab initio transition state, the ab initio calculations, the transition state theory calculation, and then the treatments of the pressure dependence. Historically, all of the uncertainty has come from the uncertainties in the energies. We couldn't calculate them accurately. But there's been huge advances in how we calculate them, so that now we can get accuracies and uncertainties of just a few tenths of a kcal, as I'll show you in a second. What I've outlined here is our particular method. You can't do electronic structure theory without doing acronyms. So I've got some acronyms there. I'm not going to take you through them, though. Those people that know that these are very time-consuming calculations. It takes days of CPU to get one energy. And we might have to calculate thousands of energies in a simulation. We can apply this approach up to about 34 electrons, which is about 5 heavy atoms, 5 carbon atoms. If we try to go to a few more, we have maybe 7 or 8 heavy atoms. We can cover essentially all of the prototypical reactions of classes of combustion. So this sort of method doesn't let us do a big biofuel, a big bioester, but it lets us do representative reactions in all the classes that we're interested in. And so it's particularly useful as we build up our knowledge base. Another key member we have at Argonne as part of our combustion chemistry group is Branko Rusic. He's developed an outstanding way to try and determine thermochemical properties. It's the approach that he calls active thermochemical tables approach. In this approach, he collects all the available experimental and theoretical data regarding thermochemistry of a set of species. And he makes sure that the thermochemical properties that you derive from that data are all self-consistent. That requirement of self-consistency leads to a huge reduction in the estimated uncertainties of your values. And so he's able to get really high accuracy active thermochemical values for many species. He's applied that approach now to about 150 species that are of relevance to the core foundational fuels mechanism, C0 to C3. This plot here shows you some of the uncertainties in those estimates. They're mostly on the order of 1/10 or 2/10 of a kcal or less, but they're not zero. And that actually turns out to be a significant part of our uncertainties. If you look here now, I'm showing here a comparison between the ANL0 electronic structure-based calculations and these active tables values. And the RMS deviation is 0.16 kcals. As I'm saying, the distribution, the uncertainties in the active tables values are a significant fraction of that, which then makes it difficult to determine. Really, when you determine uncertainties, you want to compare to true values, but you never know the true values. So in this case, we're using active thermochemical tables as a surrogate for the true values. If the uncertainties in your surrogate are comparable to the discrepancies between your procedure and the surrogate, then you can only really say that your uncertainties are of the same sort of order of magnitude, and that's almost where we're at in this case. In much of the combustion chemistry work, it's very common for people to use something called CBS-QB3. It's, again, just some acronym. It's much less time consuming. It might take an hour where my calculation might take a few weeks. but there you do sacrifice a significant amount in the accuracy of that calculation. We're comparing here 150 different species heats of formation calculation. Another approach that's kind of intermediate between these two is something called G4, which was developed by John Pople, a Nobel Prize winner for electronic structure theory. All right, so that's the kind of accuracy we can get for the heats of formation, and that's nice. But when we do rate calculations, we actually need to know what the accuracy is for the transition state. But nobody knows what transition state energies are, so we can't do the same kind of analysis. I don't have any reference values to compare to. But what we can do is go to the next step and go and implement our transition state theory and calculate the rate constant and compare that with experimental measurements. I picked this system to study for this symposium. I could have picked any number of systems and would have got the same kind of result. This is not an atypical result. What you see here is that our agreement is within the accuracy of the experiment. It's hard to say it's hard to say what the error is, at least at sort of 400 Kelvin and higher. We're going through the data points within their error bars. The experiments would appear to have about 10–20% uncertainty, and so maybe that's the kind of uncertainty we have in our theoretical prediction. I'm not adjusting any parameters to get this agreement. We do have some discrepancies here at lower temperature, maybe 50% or even factor of 2 sorts of discrepancies at lower temperature. And that's because our treatment of tunneling, something called the Eckart model, is not very good. One can do better tunneling treatments, but tunneling is something that's of key importance, sort of room temperature up to about 600 Kelvin. And it gradually decreases in importance. So I don't generally put a lot of energy into doing tunneling calculations. Much more important is trying to get good partition functions, good transition state partition functions that treat anharmonic effects, et cetera, well, and have good reference harmonic frequencies. That kind of calculation is not one we can do for all systems, and we want to try and do larger systems. We're just beginning to do work on extrapolating up to larger systems. These are not really much larger yet, but that's because we're just developing a code and exploring it. Carlo Cavallati is a sabbatical visitor at Argonne this year, and him and I and Matteo Palucci, who's here in the audience somewhere, I believe, have been working to develop a code that will let us do this more or less automatically, and we're using more approximate methods, more standard sorts of methods, and looking at what kind of accuracy we get for some system. What you see is sort of a factor of 1.5 sorts of uncertainties. One of the nice things is that when you look at this reaction, you see I didn't plot any experimental data. It's very hard for experimentalists to measure, I'm not sure that it's possible even, rate coefficients for HO2 abstracting from a fuel. But yet you see them coming up with significant sensitivity coefficients in many modeling studies. And so they need to have that data. But I have never seen a real rate coefficient measurement for an HO2 abstraction. And the basic problem is, first, the rate coefficients are very low. Look at the magnitude of these. They're orders, 10 orders of magnitude lower than for other abstractors. And experimentalists have problems measuring things that are that slow. You could increase the temperature to where they get to be larger, but as you increase the temperature, the HO2 radical decomposes faster than the reaction happens, and so you have problems. I know Ron Hansen is thinking about ways to measure it. Maybe he will succeed in the near future. But for the time being, the only way we can get these rate constants is through theoretical predictions. So I just talked about abstraction reactions so far. That first reaction, the thing that converts our fuel to a fuel radical. There's many other classes of reactions. One of the key classes of reactions are barrierless reactions. So, for example, the R plus O2 reaction that's the key to the low temperature branching is a barrierless reaction. Historically, that was a difficult problem to treat for theory because, first of all, our standard methods, what we call single reference electronic structure methods, are not applicable to the transition state region of radical recombination of barrierless reaction. You have to use multi-reference methods, which are much, much less black box. Basically, anybody could run a couple cluster calculation of a stable molecule I could teach you how to do that in 10 minutes, sorts of things. Trying to learn how to do good radical multi-reference electronic structure calculations. It takes years and not a whole career of training. So that's one of the problems. And Larry Harding, as I said, is a real expert at that, and he's taught me a lot, and we've learned a lot, and we've developed methods for doing that. Another problem is that because there is no real saddle point, you have very highly anharmonic modes, and we have to treat the full coupling of all the anharmonicities of these modes. Together, Larry Harding, myself, and Yuri Georgievsky developed a method for doing this about 15 years ago, and we applied it to a whole series of reactions. First of all was alkyl reactions. This result shows, the black line shows the result of our prediction for that. And the experimental data in this case, which is only now just catching up with us, whoops, goes nicely through those data points. There's been recent experiments from Lev Krasnoporov, and also the Mike Pilling group has reanalyzed some of their experiments. There's some ambiguity in how they treat some cross-section for the absorption that they use to observe the reaction. So there's some ambiguity, which means that there might be a 30% discrepancy, but more likely, since we agree well with the Krasnoporov data, our predictions are quantitative. We've done this sort of calculation, this sort of comparison for tens or maybe even 100 different radical reactions. And this is the kind of accuracy we generally find when there is experimental data. But there is generally very little experimental data, because to measure these rate coefficients, you need to produce two radicals. And there's extremely little data at combustion temperatures, because at the same time, you get all sorts of secondary chemistry that goes on, and it's just hard to isolate things when you get up to combustion sorts of temperatures. Until recently, we've refused or sort of just not applied this method to looking at radical plus O2 reactions. Well, you might say, well, why not? Well, that's the most important class. Why are you not doing it? The problem is, when we do our multi-reference calculations, there's two different approaches that one can use. They should agree. For R plus O2, they do not agree, and there's significant discrepancies. And those discrepancies lead to such large discrepancies or variations in our rate predictions that we don't find them to be particularly useful. But recently, with Franklin Goldsmith, we found a way to try and bypass that problem. And that involves thinking about the excited electronic state with our high-level single reference methods, and then using multi-reference methods to look at the spin splitting. That approach gives then a much better consistency between our two different methods for calculating the potential energy curves. This is just showing here that the energy for the ethyl interacting with O2 is a function of how far apart the two moieties are, and the different curves are showing you the different methods. The red and black are the two key methods, and the dotted lines are what happens if we go to this improved method. And now our discrepancies are down to a few tenths of a kcal. When we then turn those into rate estimates, we now have still some variation in our predictions, but that variation is, if we took the average of them, would be only about plus or minus 20 to 30% at the key combustion temperature. It looks like from this comparison that CAS-PT2, which is the one method that we use, is probably the better method. And we keep seeing that and are starting to presume that that may be the best method. Well, now that we've got this method, we can look at a whole series of radical oxidation reactions. So we've started looking at vinyl plus O2. Feng Zhang, who's giving a talk later, has looked at larger PAH radical plus O2 reactions. There's basically no real limit on the size of system we can look at with this method. It gets to be somewhat CPU intensive. We have to calculate tens of thousands of electronic structure points with this method, which is quite a large sounding effort. But the reality is you can parallelize that up and use each different processor on your massively parallel computer to get these kind of rate constants in a matter of a day or less in general. What I was looking at there in these reactions, various reactions, was just the high pressure limit. But almost all reactions in combustion are pressure dependent. And we need to understand that pressure dependence. For the most part, the theory has treated that part as empirically. As I talked about the simple model with Leonard-Jones collisions and exponential down energy transfer. If we have a set of data, we can We can choose this parameter so that we get a nice reproduction of experimental data. That's nice, but it's not very satisfying to the theoretician who wants to try and predict that a priori. And it's really not very nice when you think about trying to look at a system for which there is no experimental data, or even more simply, when you try and extrapolate to the temperatures of combustion, where there's almost always no data on the pressure dependence, or at least very limited data on the pressure dependence. You can do empirical things, and we've sort of developed an understanding over time of the size dependence, the temperature dependence, and the collider dependence, but that still leaves you with about a factor of 2 uncertainty, and we really want to do quite a bit better than a factor of 2 uncertainty. So the key step forward in this was realizing, with Aaron Jasper, realizing that, you know, he can calculate those energy transfer rates. It turns out it's a little bit more, with trajectory simulations, it's a little bit more complicated than just calculating energy transfer, though, because when you think about a molecule between collisions, it doesn't just conserve its energy, it also conserves its angular momentum. And your rate constants depend then on what your energy and angular momentum are. So we have to keep track of both the energy and the total angular momentum of the system and how that changes as a result of collisions. Once we do that, and we put that into a new master equation where we treat both parameters, we can then make a priori predictions of the rate coefficients. This plot here is showing our a priori predictions for the methyl plus H goes to methane system. This is an important reaction for methane combustion, for example, and really in many other systems, again, because it's varying the H concentrations, and H concentrations are central to that high temperature chain branching, H plus O2. But what you see is we get within 10 or 20% agreement. Again, it's hard to tell. We don't have the absolute numbers. We have experiment as a surrogate, and we're more or less within the error bars of those measurements. Another system we looked at is the vinyl system. Here we're able to look at both the decomposition, which is going on at quite high temperatures, 1,000 Kelvin more or less, and we get, again, without varying anything, perfect agreement with the experimental data within the error bars. At lower temperature, we appear to have some kind of slight underestimate, but it's only at about the 20% level. And at low temperature, again, our Boltzmann factors become more uncertain, and so it's not surprising we might have some minor discrepancy. One of the things you see here is the difference between these two curves is the difference between assuming that angular momentum is statistically distributed after each collision and properly treating it. And so we see really we have a factor of 2 lowering of the rate constant. You might ask, well, why didn't we learn this long time ago? We've been modeling pressure-dependent reactions for 30 years or so since Troas formulated his approach to representing things. And the answer to that would be simply, well, we've been treating this all with an empirical parameter. You can adjust your empirical parameter to give you whatever you want, and then you don't learn what the fundamental physics are. And this is going to be important as we go forward, because now we can look and think about things where channels are in competition with one another and expect to get real and proper representations of the pressure dependence for that. More importantly, we can start to think about different colliders and presume that we can really make valid statements of how your pressure dependence changes with different colliders. That's important in thinking about lots of the new combustion schemes like chemical looping and mild combustion, oxy-fuel combustion, and so on. With this approach now, we started looking, of course, at the key combustion, the most important pressure-dependent reaction in combustion, H plus O2 plus M. That's of key importance because it's competing with our chain branching channel. If we got everything combining to make HO2, then we can't go and produce our chain branching. And so almost every system you look at, you'll find a strong sensitivity to this reaction. Here we have results for 300 Kelvin, and we see that our a priori predictions are, again, in quantitative agreement with experimental data. There's some minor discrepancies with the best fit models, and that may have some interesting ramifications for the overall combustion process, but we're still in the midst of producing these results, so we haven't started exploring that yet. It is still a work in progress. That result was for 300 Kelvin. Of course, in combustion, you don't really care just about 300 Kelvin. You care much more about higher temperatures. But there's not so much experimental data to make such beautiful comparisons. Here we show an attempt to compare across a wide range of temperature and pressure. We The experiments are sort of randomly varying pressure. We can't do the comparison as directly, so we just associate the nearest pressure of the experiments with the corresponding color of the theoretical calculation. And it looks like the agreement is very good again. As I said, we're really interested in going on to different kinds of colliders. We've started and done calculations for helium as a bath, nitrogen as a bath. We get, again, good agreement. One of the things you find is that the relative efficiency of different colliders varies with temperature. Currently, there's no way to put that into a chemical mechanism with ChemKin. We've been prodding ChemKin a little bit, ANSYS, and recently they've told us that they're going to release a distribution. In their next distribution, you should be able to put proper temperature-dependent collider efficiencies in. When I talked about this work in Avignon, Tiziano Faravelli came up to me and said, we want to put that in open smoke. And I believe they've already done that. So if you're interested in doing simulations with proper temperature-dependent colliders, you can talk to him. Another change in general is that you don't usually just have one single minimum on your potential energy surface. You have many different minima in a typical combustion reaction. Peter Glarborg and Jim Miller have spent years developing mechanisms for understanding thermal denox, understanding nitrogen chemistry. And that process is a great example of the iteration between theory, experiment, and modeling to try and come to a high accuracy fundamental description of the chemistry. One of their key reactions that they thought about and that they were really concerned about was the reaction of NH2 plus NO, and we have to worry about the chain branching between HNN and N2 plus H2. Huge number of experiments trying to map this out. The red dotted line was our best sort of model thing where we had a large and substantial variations, adjustments of theoretical parameters, 4 kcals in some barrier heights. This blue line is now our best current prediction, which goes nicely through all the points, and it's nice to see that a purely theoretical description can do well for that. Sometimes we have an interesting situation where the electronic state of one of your species, one of your reactants changes. Oxygen atom is a good example of that when reacting with alkenes. You force form things on a triplet state. That triplet state can then couple to a singlet state, which brings you down to very much lower energy, potential energy surface points. And Aaron Jasper has developed methods for treating this non-adiabatic dynamics. We're going to give a talk about that later in the symposium. What we find here is, in this case, incorporating these effects makes a significant and improvement in the agreement for the ignition delay that one models for ethylene flames. My work has benefited greatly from collaborating with numerous engineers. I haven't shown all of them here. The list just goes on, and in each collaboration, I've gained a lot of understanding and so on. And when I think about what's involved in making progress, it's really this collaboration between engineering and science that's going to be central to the final stage of developing good combustion modeling processes. I just want to highlight here Mike Burke and Franklin Goldsmith were two key collaborators of mine, postdocs in my group, and Nicole Labbe and Raghu Sivaramakrishnan, and they've been central to a lot of the work going on in my group lately. One of the first things one of the more complex systems we've tried to understand is propane oxidation. Here we have N-propyl plus O2 as the first reaction step. We develop and map out the potential surface and make rate constant predictions. Well, one of the things we realize that's important as we're trying to develop better understanding of modeling is what are the uncertainties. We collaborated with Alison Tomlin and did some high-dimensional model representations based on thousands of simulations of the rate coefficients with varying parameters. And we end up with 2 sigma sorts of discrepancies about a factor of 5. That was from 2012, which doesn't seem so long ago. But if I were to apply the kind of things that we're talking about now, I would reduce each of these uncertainties by about a factor of 2 and probably get that sort of overall uncertainty. That's the first step in our RO2 QOH mechanism. The next step is to add O2 to QOH. The key pathway here corresponds to going over this barrier and losing an OH. This is very exothermic. One of the questions that Mike Burke and Franklin and I decided to try and address was whether or not this highly exothermic reaction can have a large change in the, can yield a direct dissociation of this product. And so what I've shown here is a trajectory for this transition, for going over this transition and going on to products. The H here transfers, and then we're going to see an OO bond fission. Can you play the movie, please? I guess we'll skip the movie. I don't have control over it. What we do if we run those trajectories, we see the distribution of energy in the two species. We can do that thousands of times, get the overall distribution, and calculate the probability of dissociation. The next step in the R2QOH low temperature pathway is to have a decomposition of our ketohydroperoxide. This path is supposed to go up here to lead to an OO fission and get our chain branching. Don Trular and Bill Green found that there's actually a lower energy pathway, 15 kcals lower. You might wonder, well, how can this be happening? That sounds like disaster. This is so much lower. Isn't that going to be the dominant pathway? But when we put things into our calculations, entropy is a very important part that you shouldn't forget about. And so even though you've got much lower pathway, by the time you get to 400 Kelvin, 500 Kelvin, this is actually the dominant product. We put all that together, and together with Bill Green and his group, we start to model the overall propane ignition delay. This is probably the most fundamental description of first stage ignition, and we expand that to larger alkynes and so on. It gives us an opportunity to really start learning things in detail about the whole low temperature branching. One of the things we see is that some of these reactions can be occurring promptly. For the study that we looked at in propane, it's only sort of marginal importance. But when we looked at it and thought about it some more, Raghu in particular and his postdoc Nicole were thinking that this should be very important in the abstraction process. So we start with formaldehyde here. We abstract an H with an OH. We go down here to HCO plus water. This state is low enough in energy that where we start here is higher than the dissociation to H plus CO. We try and take account of that with trajectory simulations. We're able to predict the probability of this prompt dissociation. We can put that into our mechanism and think about all HCO reactions. And what we find then is that you get 15% sorts of changes in your predicted flame speeds and also significant changes in your ignition delays and speciation profiles. These particular cases, making that change makes the mechanism work worse, which sounds like a problem. Sounds like we're not making progress. But what we have to realize is that this has to be an iterative process. Now we go back and there's something else wrong with the mechanism. We have to figure out what that something else is. We can also look at PAH formation. Alex Mebel has looked at that and had a talk about that. One of the things we see, we can do quite a bit better calculations of that. We see that there's a strong pressure dependence to our kinetics. Even for large pH species, we have a strong pressure dependence. And we need to use caution then when using low pressure flame speciation to validate it. It's great to use the low pressure flame speciation to validate your theoretical model, but you have to make sure that you include pressure dependence or you'll end up with dramatically wrong results. I've been trying to emphasize and have been telling you about the value of theory and how we've reached the point of being predictive. That's not to say that experiment is not useful. All of the work I've been doing over my career has been wonderfully motivated by experimental interactions. And again, the National Lab System has given me an opportunity to interact with some really great experimentalists, and they have been central to my developments. The last thing I want to say in that regard is that Mike Burke came to our lab and said, let's think about really experiment and theory on an even footing, and let's think about the uncertainties in those. And if you think about those uncertainties, you can develop much better understandings of the overall process. In this particular case, he developed a good description of the OH plus HO2 reaction. My vision of the future is that we start to make better use of the extremely large computational abilities that are available. We don't use anywhere near the computational power that CFD people do. As we start to do that, we're going to have to automate some processes. Work in that area is starting to happen, but we're not there yet. And I've started to join that game a little bit. Our programs that we use are starting to be made available, and we're intending to do more of that in the future. I just want to close by making some quick summary of the progression in perspectives on theory. Jim Miller's lecture in '96, he really saw the explosion of usefulness of theory that was going to come about. Al Wagner was seeing that the value and emphasizing the value of the continued interaction between theory and experiment, and that will always continue. Miller, Pilling, and Troll were a little bit more cautious, pointing out the need to continue to tune input parameters. I started seeing this future that we're really getting to now in 2011 and thinking that we could get accuracy to about 20 to 30%. And I'm seeing that in lots of calculations now. So my belief is that this long sought for a priori prediction of rate constants with accuracies that rival those of high quality experiments is now here for many classes of prototypical examples of combustion reactions. We still need to work more. There's lots of progress we need for larger molecules. But if we can keep on doing this, I think we'll be able to say, as Al Wagner did, that we're at the point where coupling with advances in computational fluid mechanics will usher in the kind of powerful and realistic simulations of practical combustion devices. I should close by noting my generous support I've received from funding from the Department of Energy. Yes, and thank you for your attention.
Thank you, Stephen, for a wonderful talk where you presented a very complex topic with clarity and rigor. Jürgen Trow years back has predicted that in years to come, the prediction of reaction rate constants for elementary reactions will be done with more accuracy than could be done experimentally. And it looks like Stephen has already proven him right. So thank you very much. Unfortunately, we're not going to have time for questions. We're already over time. So we'll present Stephen with the